I'm making this short video to talk a little bit about the critical path method and show two examples of how to use it that I've prepared. Before I do that, I want to explain really quick what I'm doing is with the critical path method, we're trying to find the earliest time that a project can be completed, and the earliest time that each task in the project can be completed drives that. We also then, we do kind of a forward pass, finding the earliest possible time that tasks can be completed. Then we do a backward pass where we're asking the question, what is the latest that this task can be completed without delaying the entire project? Now, you'll see different notations, and I wanted to show you that really quick. I believe the book uses a notation where they make a circle, and the circle might have the identifier for the task and might include the duration and number, like say 5 hours or 5 days. And then when you go through the project, they sometimes will put the early start time here, the early finish time up here, the late start, and the late finish. Sometimes when I teach this, I have taught it in the past, and some books use an ID, a duration, and then I would make a little X by the box. It would include the same information, early start, early finish, late finish, and late start. And one book I used a few years ago that I really liked did this. It drew a box for each node instead of a circle, and in the box put the ID, the duration, the early start, the early finish, the late finish, and the late start in the box. It doesn't matter which one you use, any way you want is fine. I like to use this bottom method simply because it keeps things a little bit neater on your paper. So in the examples, I'm going to do it this way instead of this way or this way. But it doesn't matter how you do it on an exam, do it however you want. The way the examples are in the book, and even the examples that I'm using here, is I actually have a sheet where you can fill in the early start, the early finish, the late start, and the late finish. So it's all here for you to do any way you want. But drawing the network diagram makes solving these problems much simpler, and I like to use network diagrams that have boxes that look like this because it's all contained in one place. So here's the first example. It says, consider the following list of project tasks, draw a critical path diagram and determine the critical path, and slack times for all activities. Which tasks, if any, are candidates for crashing, and how do you decide whether it makes sense to crash a task? All right, so first off, let's draw the network. So in this case, our first task is going to be task A, and you can see it has no immediate predecessors. So I'm just going to put task A way over here. I'm going to draw a box just because I think it looks neater. I don't have the best handwriting anyway. Its duration is 1 day. So there's task A. Now, I noticed that I have 3 tasks, B, C, and D, that all have an immediate predecessor of A. So I'm going to make 3 boxes here, make it just a little smaller, only so that it fits on the paper. Hopefully large enough that you can still see it well. I'm drawing arrows. Sometimes people forget to put heads on their arrows for tasks. I think they're really important. So if it's a very complicated network, you don't get confused as to which tasks are actually your predecessor tasks. Let's see. Yeah, we'll just label them the way that they are. B, C, and D. 2 days, 3 days, and D is 5 days. All right. Then we see that task E has predecessors of both C and D. So I'm going to draw a task E here. It requires both D and C be done before it can start. It has a duration of 3 days. I have a task F that just requires that B be done. So put F here. It has a duration of 2 days. My arrow. G requires that F be done. It takes 1 day. H requires that both takes 1 day and requires that both G and E be completed. And finally I have a task I. Task I requires only that H be done. That's my whole network. I have all of my tasks identified. I have a node for each one. I've drawn them as boxes instead of circles, but they're just nodes. And I have the duration for each task. Now I'm ready to apply the critical path method to figure out how quickly I can finish the project. So to do that, I move through the network from the beginning to the end, asking the question, what's the earliest this task can start? Now, because task A has no predecessors, task A's early start is time 0. I'll maybe make another box here just so we can have a key. Remember what I'm doing here is this is where the duration goes. And this is where the early start time goes, which is the earliest possible time the task can start. Here's where I put the early finish, the earliest time that task can finish. Then I'm going to put the latest that this task can finish without delaying the project there, and then subtract the duration to get the late start. All right, so for A, it can start at time 0. If it starts at 0, the earliest it can finish is time 1, 0 plus 1. Now, because A can be over at the earliest by time 1, that means that task B could start by 1, and if I add 2 to 1, it could be over by time 3. Task C could also start by 1, and it could be over at the earliest at time 4, and task D could start at 1 and could be over at the earliest at time 1 plus 5, which is 6. Now I come here. If F's only immediate predecessor is B, it could start as soon as B is done, which is time 3. It could be done at the earliest at 3 plus 2, which is 5. G I can do now as well. G could start as early as time 5 and could be over as early as time 6. Now I can't do H yet because I don't know E. H can't start until both G and E are done. Even though G could be done as soon as time 6, E we don't know yet. So we got to do E. E's earliest start is going to be the maximum of the early finishes of all its predecessors. It has 2 predecessors, C and D. The latest of these 2 early finishes is 6. Because even though C might be done by time 4, E can't start until time 6, because both of these have to be done before E can start. So I'm going to put a 6 here for its early start, add 3 to get 9 for its early finish. I come to H, same story here. G could be done by time 6 at the earliest, but E can't be done until 9 at the earliest. So the largest of those, the earliest that H could start because it needs both done, is 9. It could be over by 10. I could start by time 10. The earliest it could end is time 12. All right, so that's the forward pass. That tells us the earliest possible time that each of those tasks could start and finish. And it also tells me the earliest possible time that the project could be over would be time 12. Now I'm going to go backward through, they call this the backward pass through the project, determining the latest time each task can end without delaying the project. What that's going to do for me is it's going to tell me which tasks are on the critical path. Tasks on the critical path are critical to be done on time or the whole project is delayed. Other tasks are said to have slack, meaning there's some flexibility with them. And this will help us see which tasks have slack. So to do it, I'm going to start by saying, well, what's the latest that this task can end? The last tasks in the project. I start with them, and this only has one final task. Task I has to be over by time 12, or the whole project is delayed. So I'm going to add a 12 there. If it's not done by 12, then the project will be late. If there's a 13 there, then it's going to be over. I subtract the duration of 2, and I end up with 10 as being its latest start, or late start. I come to H, and I say, what is the latest H can finish without delaying the things behind it? To do that, you look at the late start of its successor tasks, and you're looking for the earliest late start. Now, there's only one, so it's easy. It's a 10. 10 minus 1 is 9, so I'm good there. Now, I come here to E. I ask, what is the latest that E can end without delaying H? Well, H has to start by time 9, so this better be a 9. Subtract 3 from 9, and I get 6. Now, if I come up here to G, G could end by time 6, but it has to be completed by time 9 or it's going to delay H. So the late finish for task G is equal to the minimum of the late starts of all its successors. It only has one, so it's easy there. It's a 9. Minus 1 is 8. Now, if I come to F, F has to end by time 8 or the whole project is delayed. So that's an 8. Minus 2 is 6. And B has to end by time 6 or the whole project is delayed. 6 minus 2 is 4. So it has to start by time 4. Now I can't do A yet because I don't know about C and D. So I'm going to do C and D next. C has to end by time 6 or the project will be delayed. Minus 3 gives me 3, so it has to start by time 3. And here, D must also end by 6 so that E can start on time. 6 minus 5 is 1. Now for A, I'm going to look at the minimum of the late starts of all of its successors. That would be a 4, a 3, and a 1. The minimum of those is 1. 1 minus 0 is 0. All right, so now I'm done. I still need to find the slack. The slack is defined as being the difference between the late start and the early start, or the late finish and the early finish. So in this case, they're the same. So the slack for task A is equal to 0. The task for task D is equal to 0. The slack for task E is equal to 0. H is equal to 0. And I is equal to 0 because they're all the same. That tells me that my critical path is equal to A, D, E, H, and I. The other tasks are going to have slack. Here my slack is equal to 3 days. Here it's equal to 3. Here it's equal to 3. And this one, C, has a slack of 2. So it is possible you can have multiple critical paths through a network. This project only has one, conveniently. This is my critical path. Why is that important? Well, you can think of these tasks on the critical path as something like a bottleneck. If any of those tasks are delayed, then the whole project is going to be delayed. Further, if we want to crash this project, crashing means speeding up the project by throwing extra resources at it, then we basically add more people or more machines or whatever to make the project, that task, done quicker. But if I speed up a task that's not on the critical path, a task that already has slack, so for instance, if I reduce this 3 to a 2 or a 1, or this 2 to a 1, it doesn't help me. The project's still going to take 12 days. So it's not useful to reduce the duration of any task not on the critical path. Only tasks on the critical path result in savings to the project. And so you would never crash a task that's not on the critical path. Now, the way that you actually crash a project is you crash a day off a task, and then you redo the critical path method to see if it really bought you the time that you need. The reason why you have to do that is sometimes when you start crashing things, they might eventually not be on the critical path anymore. Or you might have 2 critical paths. So in order to crash a day off the project, you need to shave a day off of each path through the network. But that's the critical path method. It's a very quick and easy heuristic to determine how quickly a project can be done, what the critical path is, and which tasks have slack, and how much slack they have. Fairly easy. And usually the first part's easy, going backward through takes a little practice. So I'm going to do a second problem for you, for those who want that. Here's another network. And if I wanted to, so now, if I wanted to, I could transfer all of these numbers up here. So for task A, we had an early start of 0, an early finish of 1, a late start of 0, a late finish of 1, and the slack was equal to 0. For task B, we had an early start of 1, an early finish of 3, a late start of 4, an early finish of 6, and the slack was equal to 3. And I could transfer all of that, but I'm not going to make you watch all of that. All right, here's another one. I'm going to do it the same way. First thing I'm going to do is draw the critical path diagram. One thing you'll notice in this particular task, or this particular project, is that there are 2 tasks, both A and B, that have no immediate predecessors. So I'm going to stick A and B over here on the side of the project. A has a duration of 4 days, B has a duration of 3 days. Now, sometimes when you're drawing a network, if you want it to look nice, you maybe draw it once to kind of get an idea of what it looks like, and maybe you redraw it and it turns out nicer. That's fine. There's software that will do this and also do all of this mathematics for you. Primavera, Microsoft Project, and others. But it's useful to do it yourself once or twice so you know what's going on. So task C has an immediate predecessor of A. So put C here. C's duration is 3 days. We have B, which requires, D requires both B and C be done. So I'll go ahead and come out here and put it here. I could put it straight underneath, but here's D. It requires that B and also that C be completed in order for it to start. D has a duration of 4 days. Task E requires only that B be done. So here's E. It has a duration of 3 days. We have task F. Requires only that D be done. F has a duration of 4 days. G requires that F and E both be done. So G has a duration of 3 days, requires F, probably should have drawn it to the side, but 2 arrows going into the box. And then finally you have H, which requires only that F be done before it. So H, and it has a duration of 1 day. All right, so now I'm ready to apply the critical path method to this problem. Both A and B could start at the earliest at time 0. A could be over by time 4, 0 plus 4. B could be over by time 3, 0 plus 3. C has only one immediate predecessor of A. A can be over by 4, so I have a 4 here. That's the earliest it could start, and its early finish would be 7. D has an earliest start of the maximum of 7 and 3. Even though B could be done by 3, C isn't done until 7. So I've got a 7, be over by 11. E could start by time 3 and be over by 6. I can't do G yet because I don't know about F, but F could start by time 11 and could be over by time 15, which means G's earliest start is 15. Its earliest completion is 18. H could start by time 15. Its earliest completion would be 16. So the earliest that this project could be completed is time 18. All right, now I can go backward through the project. I'm going to start by saying, well, what's the latest that these final tasks can end without delaying the project? And it's going to be a late finish of 18 and a late finish of 18. Because if this is over any later than 18, it will delay the project. But it doesn't need to be done by 16 because it has no successors. So 18 minus 3 is 15. 18 minus 1 is 17. I come here. F needs to be done in time for both G and H to start. And so you're looking at the minimum of the late starts of H and G. That would be 17 and 15. The minimum of those is 15, so this has to end by time 15, which means it has to start by time 11. D has to start by time 11, or end by time 11, so it has to start by 7. E has to be completed by time 15, which means it has to start by time 12. B has to end by the minimum of 7 and 12, so it has to end by time 7, which means it better start by time 4. Up here, C has to end by time 7, which means it has to start by time 4, which means A has to end by 4, so it has to start by 0. So I've finished the method. Now I can calculate my slacks. For A, my slack is equal to 0. For C, it is equal to 0. For D, it is equal to 0. For F, it is equal to 0. For H, I have slack of 2. For G, I have slack of 0. And for E, I have slack equal to 9. And for B, I have slack equal to 4. So the critical path is A, C, D, F, G. And there is a critical path. That means there'll be a path through the network that has all zeros. Perhaps more than one path, but in this case, one path. So which steps would be categories, which tasks would be candidates for crashing? The answer would be A, C, D, F, and G. Which tasks would not be candidates for crashing? B, E, and H. Because if I crash B, E, or H, they are already not on the critical path anyway. So I'm basically spending money, spending time to shorten things that don't actually make my project be completed any faster. So those are two simple examples of how to apply the critical path method, how to find the early start, early finish, and late start and late finish for the different tasks, and find the slack, and a little bit about crashing and what that means. I hope that those prove helpful as you're learning to use the critical path method yourself. I will eventually make another video for those who are interested on how to use PERT, the Product Evaluation Review Technique, that relaxes the assumption that we know exactly how long each project takes. But not every class that I teach requires that you learn to use PERT. Thank you.